Okay. So it's this other units business down here. Most of it's true, a little bit of it's wrong. So this part's true. I'm skipping the wrong part. I'll come back to it. 1 calorie is 4.184 joules. So a calorie is just a different unit for energy than joules. A food calorie is a kilocalorie, which is 1,000 calories, which is 4,184 joules, which is kind of interesting, really. If we jump down to one of these problems you'll have to do for homework, it says a Snicker bar contains about 260,000 calories of energy. That's true. And a calorie is 4.184 joules, and a joule is a Newton meter. So how heavy is a Newton? Banana. And if you wanted to do 1 joule of work, you'd have to lift a banana 1 meter. So with 1 calorie, you could lift a banana 4.184 meters. With 260,000 calories, you could lift bananas lots of meters, right? So that's a lot of bananas you could lift with just 1 Snickers bar. In fact, if you ate a banana, if you ate half the banana and used like all that energy to just lift the other half of the banana up and down, just think of all the entertainment you could provide yourself. So anyway, I think that's kind of kind of bizarre there. It just seems like it's way too much energy, but it's true. So these, yeah, we're not 100% efficient. I can't remember it. It seems like I looked up the efficiency of a human being, and I think it compares to a car. But it probably depends on what we're doing. Efficiency, I'm going to do mechanical efficiency, percent efficiency of human. So according to the AI, around 25%, which is actually more efficient than most combustion engines. A gas vehicle. This is probably going to be, oh no, it's a little higher, 20 to 35%. So I guess we're about the same. Sorry, 25% was lower than what I was thinking. So we're kind of the same. I've lost my page. Oh, it wasn't a page. So if you are 25% efficient and you eat 260,000 calories, in this problem, it says that the dad is actually 30% efficient. He's pretty efficient. So he gets 30%, 3/10 of those 260,000 calories to actually do work with. And this question is about dragging his daughter around. Inspired back in the day when I wrote this, I used to drag my daughter around in sleds a lot. And I don't know, drag her all over. So back to this. A food calorie is 1,000 calories. So it doesn't say on the Snickers package it's 260,000. It just says 260 calories. And one calorie is 4.184 joules. Here's the problem. Where it says 1 joule is derived from the amount of energy required to raise a kilogram of water by 1 degree Celsius, that's not right. But I see what I was thinking. Does anybody know what should really go there instead of a joule? 1 kilocalorie. Yeah. And who was the person who did this experiment? It was Joule. So it was James Prescott Joule who did this experiment. And somewhere I've got a link to his apparatus. Apparatus, right here. Joule's apparatus. So he had a weight and he had a pulley, and the weight was attached to a string around the pulley, wound around this, and there are some paddles down here, and this is water in an insulated container, and there's a thermometer, and he just let this thing fall, and that caused the paddles to go around, and then he measured the work done by this, which you could think of as the potential energy it loses, and then measured the temperature change there, and he figured out that 4.18 joules of work raises the temperature of 1 gram of water by 1 degree Celsius. The kilogram of water thing comes in. If you raise a kilogram by 1 degree Celsius, that's a kilocalorie of energy, which is 4,184 joules. So just suffice it to say that if you ever need to convert, just know that you can, and you can Google it out in the real world, but on here I'll provide this on tests. But it's so you can answer questions like this, you know, the dad's exerting a force of so many newtons over a distance, so force and distance you can get joules, but then you've got calories and you've got to get them in compatible units. And to answer this kind of question, you've got to be able to calculate efficiency. So we need to go to page 12 and go over the formula for efficiency and figure out the efficiency of a possum. I just totally made this up. I don't know how efficient a possum is. But according to this example, possums are more efficient than people in combustion engines. So we have the formula. Formula is, in my experience, if you say this formula really quickly, you get it backward. It just sounds wrong when sounds right when it's said wrong. So it's energy divided by energy. What energy do you divide by what energy? There's output energy and input energy. Which one goes in the numerator, do you think?
Output.
Output. Yes, you got it right the first time. Somehow I screw this up if I'm not careful. So this is energy output, which you have to define what you mean by energy output over energy input. So if you get out, well, first of all, can this fraction ever be 1?
What?
Can this fraction ever be 1?
No. Well,
Theoretically, but realistically, no, because there's always something that steals energy away, usually in the form of heat. So if you put in like 10 joules of energy and you get out 9 joules of energy, then you've got 9/10, which is 90%. So to make it come out as a percent, multiply it by 100%. So now the possum. 10 kilogram possum. You don't have to draw a possum. I didn't draw a possum last time, but I'm going to draw a possum. So there it is, and it climbs 5 meters up a tree. So we'll show it hanging upside down because that's what possums do, supposedly. They also supposedly play possum. Sometimes they do, and sometimes they just hiss at you and try to bite you. I know this because somebody told me once to kick the possum. It'll play possum, and then we'll just put it in a bag and take it down the road to the guy who eats possums. But I kicked the possum, and it went, and I kicked it again, and it went, kicked it all the way across the cornfield. Never did play possum. So anyway, this is not drawn to scale. This height is 5 meters. And it says here that the possum uses 1,000 joules of energy in the process. So using my formula, that 1,000 joules of energy would be what? Output or input? Input. So that's something over 1,000 joules. And so we need the output. How do we get the output of this? The possum uses up 1,000 joules of energy to get up there 5 meters. So how do we calculate that output? That would be potential energy, yeah. So if the possum, it stops, and it's stopped at the beginning, so the energy that it puts into this is all turned into potential. That must be the output. And potential energy, what's the formula? MGH. So that's going to be for the possum 10 kilograms times 9.8 meters per second squared times 5 meters, and it ends up being 490 joules. So that's the potential energy in the possum in the end. 490 joules divided by 1,000 joules multiplied by 100% is it over half efficient? No, not quite. So 49% efficient. Still more efficient than humans. But I don't know if that's really true for possums. I would guess that that's pretty inefficient.
Also, it wouldn't convert all of its non-conservative work into potential energy, though, because there'd be friction on the tree and stuff.
Well, that's where a lot of this goes away. That 51% that gets lost is probably heating up the tree with its claws, poking in and doing other stuff. And also heating the possum. It's probably panting up there. Do possums pant? Do they sweat? I don't know. I don't know about how marsupials cool themselves. So let's see.
Water cooling system.
They're water cooled.
Yeah.
That's it. With fans.
AIO.
So the Atwood Machine Energy Analysis Lab. So hopefully last class you got data for these 4 blue cells. Object A's mass, object B's mass, this height, this time. And all you have to do is enter all the correct formulas into these yellow cells and have exactly right answers there. It's tricky, and you don't have to do part 3 and part 4. I don't know if we're ever going to do those, but part 1 and 2 are, well, really part 2 is enough. And I would say the trickiest thing is right at the beginning, and that's where you have to find the speed. So object A is going to fall, and when it gets to almost the ground, you've got to figure out what the speed is. If you assume it starts from rest, and then you assume the acceleration is constant, and you know the distance and you know the time, you ought to be able to get that final velocity there. So make sure that you have your own copy of this. Don't just share it with group members. If you do share it with them, that's fine, but once you get it shared, go to File, make a copy, make your own copy, and then turn that in. I'll be milling around, and if you want me at some point to confirm some of your answers, just tell me these 4 bits of information, and then pick a cell over here and tell me what you got, and I'll tell you if it's right.